qualitative analysis is the process of separating and identifying ions. Because it's qualitative, we don't have any numbers attached to it. Selective precipitation is the process by which ions are caused to precipitate. So PPT stands for precipitate. So process by which ions are caused to precipitate one by one in sequence to separate mixtures of ions. So we would use selective precipitation if we have a mixture of ions in a solution and we want to find out what percent or how much of each ion we have. So in this problem it says, how can you separate a mixture containing silver ion, barium ion, and iron 3 ion? When you're thinking about selective precipitation and how do I get those out of solution, you need to be thinking about the solubility rules that we talked about previously. And think what is insoluble while the other two are going to be soluble in something. So all chlorides, bromides, and iodides are soluble except silver, lead, and mercury. So there's our silver. And all sulfates are soluble except silver, and then there's barium. So notice I can't use a sulfate salt to begin with because that would precipitate silver and barium, and then I wouldn't be able to distinguish between those two. So the first thing I'm going to want to do is add something with either chloride, bromide, or iodide salts. So I would choose a group 1A chloride, bromide, or iodide because we know that group 1A or ammonium are always soluble. So I'm not going to have a side reaction with, let's say, sodium chloride. The sodium wouldn't be reacting with anything because it's always soluble. So the first step is I can add sodium chloride, which will cause the silver ions to react with the chlorine to precipitate silver chloride. I could have said sodium chloride, sodium bromide, or sodium iodide. And I also didn't have to use sodium. I could have used any of the group 1A metals, or technically ammonium. So now that I have silver gone, so all my silver has been removed from the solution. Now I just have barium and iron. Notice none of the solubility rules have iron, but as we said a second ago, we can get barium out. Before we get barium out, we're going to want to go in and get that silver chloride precipitate out of solution. So to do so, we can precipitate it, or filter it. So we're going to filter out all the silver chloride, so now we have just a solution again. If I didn't filter before having another precipitate formed, then I would have again the precipitates mixing and I wouldn't know which is which. So that's why I filtered out first. Now I'm going to want to add a sulfate salt because all the sulfates will be soluble except my barium sulfate. So going with that same rationale as before, I'm going to want a group 1A sulfate or an ammonium sulfate. So if I add sodium sulfate, it'll cause barium to react with that sulfate ion to precipitate barium sulfate. I can then filter out the barium sulfate. Once I filter out that barium sulfate, the barium is now gone. So I'm left with the iron 3 ion. So step 5 is technically you are left with just the iron ion. Go ahead and look at your solubility rules and figure out how you could separate a mixture of calcium ion, lead 2 ion, and nickel 2 ion. So this problem is just like the one we saw a second ago because we have lead in more than one spot and calcium in just one spot. And we don't see nickel in any of the solubility rules. So just like before, we wanted to get rid of the lead first and then the calcium, and then we'll be left with the nickel. So just to change it up a little bit, I added potassium chloride to produce lead chloride. But you could have said any group 1A, chloride, bromide, or iodide. So I could have said add potassium iodide to produce lead iodide precipitate. I would then filter out that precipitate, whichever precipitate I had made, whether it be lead chloride, lead bromide, or lead iodide. And then I'm going to add again a group 1A sulfate, so any group 1A sulfate to produce calcium sulfate. Filtering out that calcium sulfate will leave me with the nickel ion. Quantitative analysis is going to determine how much of a component is present. So I could basically do what I just did, but actually weigh those precipitates and then figure out how much barium was in barium sulfate. Then figure out how much silver was in the silver chloride to figure out the mass of my iron. So gravimetric analysis is a quantitative procedure where a precipitate containing the substance is formed, filtered, dried, and then weighed so we can determine how much of that component was present in the original mixture. So in this problem it says that we have a mixture containing sodium chloride and iron 3 nitrate. A 0.456 gram sample of this mixture, notice that this grams is of a mixture. So I can't use that mass until the very, very end because I don't know how much of it is sodium chloride and how much of it is iron 3 nitrate. It's dissolved in water though, and then an excess of sodium hydroxide is added, producing the precipitate of iron 3 hydroxide. So all of this iron is reacting with the hydroxide to produce iron 3 hydroxide. That precipitate is then filtered, dried, and weighed, and that's its mass. So that 0.128 grams is of iron 3 hydroxide. That I do know the compound. So I start with whatever thing or whatever substance I know the mass of. So if I have 0.128 grams of iron 3 hydroxide, I need to find out how much of that is iron. Because if I know how much of it is iron, then I can figure out how much of this 0.456 grams was the sodium chloride. So just like we did in the first 3 chapters, we're going from grams of iron 3 hydroxide to grams of iron. It's just a mass-to-mass problem. So I find my molar mass of iron 3 hydroxide, which is 106.87. I only have 1 iron, so the molar mass of that 1 iron is 55.87. And I had 3 sig figs so I get 0.0669 grams of iron ion. But I had iron 3 nitrate in that compound. So I'm going to start with that, and if I know all of the iron in the compound, I can figure out the mass of the compound itself. So whatever unit I started with has to go on the bottom, and I'm converting this to grams of iron 3 nitrate. So very similar to what I just did, except I have a different molar mass and it's flipped because now I have just the mass of the metal and mass of the compound on top. So iron 3 nitrate is 241.88 grams. And I still only have 1 iron, so 55.85. Multiplying and dividing in 3 sig figs, I get 0.29 grams of iron 3 nitrate. So finally, to find my mass percent of iron 3 nitrate, mass percent is mass of what I was looking for, mass of iron 3 nitrate, over total mass. That's where the 0.456 is going to come in. because that's grams of the sample. Multiply by 100, and we get our 63.6%. Which means sodium chloride must have been 100 minus that. On this problem, notice we're also calculating the mass percent, this time of zinc in the foot powder. So we're going to go through pretty much the exact same steps as what we did a second ago. So first step is find mass of zinc. In the ZnNH PO, because that was my precipitate. And then I can just find my mass percent. So I have one less step because all of the iron went to that, and I'm just trying to find the mass percent of zinc, not of a different compound. So pause the video and find your mass of zinc and then your mass percent. Restart when you have an answer. So my molar mass of ZnNH PO was 304.72. In this case, I have 2 zincs though. So it should be 130.78 on top. So 0.1755 grams of zinc, because I have 4 sig figs. So finally, for your mass percent, I put that over the sample times 100. So you should have gotten 14.63% of zinc.